welcome to this final session on AI2, where we'll be doing game searching and alpha beta pruning. So I'm assuming you guys can all see my screen. I'm sharing the Notion. Okay, cool. Let's get straight into it. So game is also called adversarial search and is a search problem where essentially your opponent has something to say about your strategy. And just like any games, there are some factors that we need to take into account to kind of describe the game and tell people like what kind of game this is. So the main four factors that we need to kind of consider when we, emulate a game is there an element of randomness? This is called determinism, right? For example, tic-tac-toe is deterministic. You can always guarantee the action. You can always guarantee the next state provided you take an action. Whereas, say, any game that involves a dice, such as Ludo or Monopoly, well, that's random, so you can't guarantee a state provided an action. You also have to factor in how many players are there. Is it single player like solitaire? Is it, two players? Is it more than two? So on. And the other key term to note here is, are you competing with the other players or are you cooperating against them? If you're competing, it's called a zero-sum game. So here we're bringing in game theory as well. But if you're cooperating, it's a positive-sum game. The reason why it's called zero-sum, you don't need to know exactly, but it's basically because if you win, that means someone else loses. Therefore, the net change is zero. Therefore, if you sum it up, it's zero-sum. Whereas if you cooperate with others, that means you can all win together, meaning, you'd end up with a net positive because no one has to lose in order for you to win. Therefore, it's a positive-sum game. And finally, the other important factor is, can you see the state? So, for example, in tic-tac-toe, you can exactly see the entire board or all 9 squares at all times. It's called perfect information. Whereas in poker, the whole point of the game is that you can't see the cards that the other player has or your opponent has. So that's where it's imperfect information or it's partially hidden state. When you have these factors, then you can decide whether implementing a game search algorithm will be effective for the game you're trying to play. So how do we formulate a game search algorithm? Well, like I touched on yesterday, it's actually very, very similar to formulating any search algorithm, really. In fact, you'll notice that all of these were involved with any search algorithm. So you have the state, which includes the initial state, which we call S0. And S represents all of the states, right? You have the actions, this is specific for a certain state. So it's like a list of actions you can take from a specific state. You have the transition function, which is actually what tells you what is the resulting state, provided you take a specific action from a certain state. Then you have the terminal test, or yesterday we called this the goal test. It's the exact same thing. It's a function to test, is this a goal? Is it an endpoint? And players, very simple, how many players are there, 1 to n. They usually take turns, that's why you gotta know. And utilities, the utility function is like an objective function. It basically tells you what your performance in a game is at the end of the game. So once you've reached a goal state or a terminal state, it'll tell you you scored this much, essentially. How well did you do? And that's everything that you need to know about a game state. So once you have these set, you can implement a game search algorithm. Here's an example of tic-tac-toe. As you can see, the initial state they gave us was this board here. The entire board, by the way, is the state. So we call this as one of the states. It's one of the possibilities that you can have at any given time in tic-tac-toe. Now, from this state, you have these arcs coming out of it. These are the actions. So as you can see, the action here would be put X in column 1, row 2, something like that, and that would be the action. And then this state here is the result of the transition function, meaning this is what you get once you apply the action to a state, and you get this essentially. And I think that's all of the ones. Oh yeah, utility. As you can see, each one has a utility a utility function result written under it. So if you look at the ones at the bottom, right, assuming we're playing as X, right, the utility for winning is 1, drawing is 0, and loss is -1. So as you can see here, for example, we have won the game, so the utility function evaluates to 1 for this state here, and that's what we mean by the utility function. I hope that's all clear how each component of a game search works and its application in a real game tree here. So this is a game tree, by the way. So when you've generated all the states from a certain state, you can call that a game tree. And, oh, one sec, I should have muted my phone. But essentially, yeah, so if the utility of all the children of a node yield the same utility, then the score is also moved up to the utility of the current node. So as you can see here, for example, the utility of this is 1, so it's going to be assumed that the utility of the one above is 1, since there's only one possible action that can be taken from this state here. Just something to keep in mind. However, this is not the same as alpha, beta, pre, and min-max, where you travel numbers up. We'll look at that later. So let's move on to min-max, right? We're already a significant way through this session. Minimax. The minimax value of a node is the utility score that'll be reached in the terminal state if both players play optimally from there on. And this can only be used when the game is deterministic, so there's no element of randomness, and it's a zero-sum game. Do we have any questions in the chat? Let me just check. Is it me? Your voice is lagging. Never mind. Is it still lagging? Is my voice okay? Seems okay. Alright. I mean, I'm hoping the Wi-Fi is gonna stay okay. I mean, yeah, okay, cool. Let's just continue then. But there's no questions as of now then. Might just be a slow connection. Okay, so yeah, you can apply the minimax system to deterministic zero-sum games, and essentially, like this is not needed, but the way it's kind of proposed is that it's a two-player game. One of the players is called Max or Agent Max, who tries to maximize his utility, whereas his ops is called Agent Min, who tries to minimize Max's utility. He's just trying to, you know, rain on his parade. And that's like the assumption behind Minimax anyway. So here we can see that it's been implemented recursively for the Minimax algorithm. So it's a very basic and simple algorithm. I've written it out in Python here. So essentially, to work out the minimax of a certain state, all we do is firstly we check the base case. The base case is that is it a terminal state? If it is, we just return the utility of the state, the utility being the score achieved of that state, as we looked at above, like these. Then if it's not a terminal state, then we check whose turn it is. If the turn of the state is player max, then we set the value to -infinity, and then we look at all of the actions that we can take from this state, and for each of the actions we decide, is the value that we currently have greater or the value of the result of taking that action. And then whichever one is greater, we return that value. And we do that for all the actions possible from any given state. Then we if the player is min, essentially we try to do the opposite thing. We start at the worst possible value for min, which is +infinity. And then for A in actions given S, so same thing, just we check that is the current value we have the minimum we can get, or is the new state we generate by taking this action the minimum, and whichever one's smaller we pick that value and return it back to the minimax function. Right, okay. It's recursive as we need to calculate the minimax of the state. As in order to calculate the minimax of the state, we need to calculate the minimax of the result of each action, which gives us new states, and then therefore we need to actually go into those states and then calculate the minimax, which involves generating more states and so on. And this all continues until we reach the terminal state, which is the base case. So this minimax is a recursive algorithm, essentially, which leads me on to the next problem, the minimax efficiency problem. And this problem states that since minimax effectively uses an exhaustive depth-first search algorithm, the time complexity is of O b to the m, where we looked at this in DSA last year. B is the branching factor, so the average number of branches per node, which is basically the average number of actions you can take from each state, average number of successes or children you can generate from each state. And m is the maximum depth of the tree. So what is the, of any path, what is the longest path that you can have from initial state to final state? In tic-tac-toe, for example, that would be 9. The longest possible, the deepest possible tree you can have in tic-tac-toe is 9, since that's after you filled up all of the spaces. There's only 9 spaces to fill. And it has a space complexity of O of bm, but that's not really a problem. So it does not run in polytime, it runs in exponential time, which is okay for simple games like tic-tac-toe, but it's completely infeasible for games like chess or Go, where there's like, millions of different states that you can have. But there's more than millions, it's like a huge number. Which is where alpha beta pruning comes in to save the day. So this eliminates exploring certain game states if we know they won't be useful for determining the best move to make, and it relies on the assumption that our opponent is playing optimally. So that's the assumption that this relies on. However, it's still correct regardless, but it basically takes the worst case scenario that the opponent is the best kind of opponent that you could have. So we have to set 2 values, right? So let alpha be the best value max can guarantee so far, and let beta be the best value min can guarantee so far. So, as at the start, the best value that max can guarantee is literally negative infinity because it can't guarantee anything. And for beta, it's positive infinity, same reason. We have a question in the chat. Makes no wrong moves. What, like the opponent? Yeah. So if we're assuming, a player is playing optimally, it means it's probably using the same algorithm that we are, and it's essentially making the best possible move based on the same metrics that we're measuring it by. So essentially the rule here is that while computing the minimum value at node n, if we find that the value at n is already worse than alpha, max will actually never choose this path. If you think about it logically, why would it choose that path? And based on that, we know we can just stop exploring n's remaining children. When we do this, you can only change the value of whoever's turn it is as you go up the tree. And essentially, as described above here, essentially this is the rule. If alpha is greater than or equal to beta at any node, you stop exploring its children. And what that means is you prune them. And it's important to note that pruning does not change the final min-max value of the root, as it doesn't actually remove any opportunity that's not optimal. So it only removes the things that aren't optimal because, well, you're never going to need them because you're going to play optimally. And assuming your opponent is as well, you don't need to explore any options where either of you have, played non-optimally. And then if good moves are explored first, then pruning is more effective. So that's what we'll try and do. It's like ordering from CSPs we looked at last time. And with alpha beta pruning, the best case time complexity reduces from b to the m to actually b to the m over 2. So it halves the depth, meaning you actually can search twice as deep as a normal minimax, given a specific level of computation. However, there is a problem with alpha beta pruning, and is that even with pruning, the full search in games like chess or Go is impractical due to the high complexity. So you actually still can't use it in chess and stuff because it's just that many possible states that it doesn't work. So here's a question, right? Give the minimax value at each node for the game tree below, right? So we can kind of just look at this logically, right? Without having to consider the alpha beta stuff or alpha beta pruning. For the first question, at least, we just look at this algorithm, right? And we compare which value gives us the best result, depending on whose turn it is. So simply, if you look at it, right, let's start here, right? Well, we need to start there, but eventually it'll lead to unknowns and give us to here anyway. And it's Max's turn. We know that Max will choose 8 because it's trying to maximize the value, so 8 would go into there. And because we're not pruning or anything right now, let's look at that. So that, for example, now could be 8. We look at this, right, and we see that Max would choose 20. So now Min is the next player here. So we know that Min would choose 8 because it won't want to choose 20 because it's bigger than 8. And then you know that 8 would be the contender from this side. So if something bigger is generated on this side, then we won't use 8, otherwise we'll use 8. So essentially we do the same thing on this side, and we choose 4 from here, we choose 15 from here, and then Min would choose 4, obviously, and now we say that 8 is bigger than 4, so 8 would go in the top, right? And now let me switch to the whiteboard to give a more comprehensive example of going through alpha beta pruning. Screen stop. And I'll need to make sure not to switch it to my MetaMask key this time. Okay, right. This is the Microsoft whiteboard. Can we see this on the screen? Okay. Let me go to switch that in OBS as well. Okay. Right. So, essentially, what we're gonna do is, right, okay, I'm gonna start writing. So, here we go. So, essentially, the goal here is, let me just get the whole thing in the field of view. So, the goal here is to obviously, not have to search the ones that you don't want to search, like you don't need to search, so you'd have to prune them, right? So here we have a tree initially, right? And what we can do is we'll start at the top. This is our initial state, so we write in the value of alpha and beta. These are both taken to be negative infinity and positive infinity respectively, as shown by our algorithm. And this is it's also not a terminal state. And then we can say here that as we assume like we're gonna go left, right? That's how we break ties. We break ties by going left. This would then also be negative infinity and positive infinity. This would then also be negative infinity. Oh, why did I put 8? Okay, right. Negative infinity and positive infinity. And finally, this would be negative infinity and positive infinity. Right. So once we've reached a terminal, right, we can see that it is Min's turn, right? Meaning the only value will change is gonna be beta, right? Because it's Min's turn. And what will that value become? So what we'll see is the two options here, right? 10 and 5. And from that, we can choose the minimum value. So, or actually not from 10 and 5. So what we do is we actually compare it with the current value being infinity. And we compare it with every single action state that we reach after performing an action. So the state we reach by performing this action would be 10. State we reach by performing this action would be 5. So what's the smallest value possible? Is it infinity? Is it 10? Or is it 5? Obviously, it's 5. So that means that we can scrap out infinity and change that to 5. And that's it for this level. We can now backtrack up to here. So when we go here, now it's Max's turn. What will Max do? Max will look at what can we do here. So are we going to compare minus infinity to 5? So out of these values, right, what is the biggest we can get. So obviously it would be 5. So we can change this to 5. Now we can, essentially, as you can see, we haven't explored this branch yet, and there's the condition for pruning it is also not reached, because as you can see, alpha is not greater than beta, and it's not equal to beta. So we can go explore this branch, and from here, let's write in what our values would be. So here, right now, right, the biggest, it just copy the values from above when you're bringing it down. So it would just go there, right? And now if you analyze these ones, it's min's turn, meaning we'll change beta. Out of these two, out of infinity, 7 and 11, it would obviously pick 7. So we change the value of beta to 7. Now, if we go back up one, right, we can now see that what will alpha have to pick? Alpha will pick between 5, negative infinity, 5, 5, and 7. So the maximum value here is 7. So we can say that it's not going to be 5, it's actually going to be 7. So that we've explored all the subtrees here and we didn't need to prune anything. Do we have any questions about how anything's working? Let me just check the chat. Bro, watch that one Indian's video for the example. Yes, I did. Yes, that is exactly, you've identified it correctly. Yeah. So essentially, they're the best kind though. Essentially, let's get back to it. So now we have we move up the states here. So we have negative infinity and positive infinity set for alpha and beta, but we know it's min's turn, so we only change the value of beta. So we look at that. What do we have? We have currently just 7 and infinity. So the smallest one out of these two is obviously just 7. So we change that to 7, right? And now we can go back and explore this, right? And if we do that, bring down the values of alpha and beta we have above. So that's negative infinity and 7. And we bring down the value here as well, so that we have alpha is equal to negative infinity and beta is equal to 7, right? And from that, we can now do the same thing. So this is min's turn. Beta will pick between 7, 12, and 8. So obviously 7 is the smallest, so that won't change. And then max will pick then. So max will see between negative infinity or 7. So out of these ones, obviously 7 is the biggest. So it'll scrap negative infinity and it'll instead pick 7. Oh no, what do we notice here? We notice that alpha and beta, right, they are the same, meaning this is a condition for pruning, meaning this child is useless. It's a useless child. We're going to prune any further branches of exploring. So we're not going to look at this anymore because we know we're not going to use it. And that's the condition for pruning. Now we could continue. So if we were to continue, we would then try and change the value of min here for beta, and essentially move that. Check which ones that. So all of them are 7 in this case, so nothing changes. And now we've finished exploring this entire subtree. And note, we did not have to actually explore this subtree here, which saved us a lot of computation. So if we move here now, we can go to the top and we can change the initial values of alpha. So this is max's turn, meaning we'll only change the value of alpha. So alpha will no longer be negative infinity. It will now be 7. Okay, one sec. It will now be 7. And then now we do the same thing with the other subtree. Would you like me to continue, or do you get the gist of it? Why did we set alpha to 7 on L3? Do you understand why we set alpha to 7 now, or do you need to explain? Okay, wait, where exactly? L3, so that 1, 2, 3, row 2. So this one here. We set alpha? Why did we set alpha to 7? Well, it's because if you explore the left tree of it over here, right, and this is min. No, we can't. We're not changing alpha on this. It's min's turn, so you'd only stay 7. You can't change alpha there. The minimum value there would be 7. Because you're comparing with the current value you already have and the 2 new values you've explored. So it's between, because it's min's turn, you're not even going to consider maxing anything, right? You have to minimize. So the minimum would be between 7, 12, and 8, and 7's the minimum there. So that's it. Does that make sense, Shay? Okay, cool. Right. So would you like me to continue? I can do a couple more rounds of this just to get it all ingrained. So yeah, we're at the top here, meaning we can now go down. So we now just bring down the values of alpha and beta that we have already. So when you go down, you literally just copy paste. So it's like alpha is 7, beta is infinity. Alpha is 7, beta is infinity. Alpha is 7. I'm horrible at writing this. Okay, beta is infinity. Right, and we go down the left path because we're choosing lefts to break ties. That's what's given in the question. So yeah, here we've reached a terminal. So we see it's min's turn. So is the current value smaller, or is 5 smaller, or is 12 smaller? So we can see that 5 is smaller than infinity and 12. So we pick 5. This value changes from beta to 5. Sorry, from infinity to 5. We move up 1, so this is max's turn, meaning we only change alpha. We're comparing alpha to 7 and 5. The maximum that we can reach is, in fact, 7, so because it's bigger than 5. And, yeah, that was infinity. This became 5. Yeah, okay. So that stays 7. We move this down now to the right branch. So this becomes 7. This is infinity. And we check over here, we have 11 and 12. If you move down a little bit, we have 11 and 12. So it's beta's turn. So is infinity bigger? Sorry, is infinity smaller, or is 11 smaller, or is 12 smaller? So the smallest one here is 11. So we pick 11 because it's min's turn. Now it's max's turn up here. So we're only going to change alpha. So in this case, is 7 small, or is 7 small, or is 11 small? Sorry, is it big? Sorry, is 7 big, or is 7 big, or is 11 big? And we can see that 11 is the biggest one there. So we can kind of get rid of 7 and just put 11 there instead. Would we not pass 5 back up as the alpha for L3 row 3 from L4 4 5? Would we not pass 5 back up? So from here, are you saying, would we pass 5 back up? No, we would not pass 5 back up because 7 is bigger than 5. So we would not pass 5 back up. Because you have to consider whose turn it is. If it's max's turn, you can't alter the value of beta. You can only alter the value of alpha. Same with min, right? If it's min's turn, you can only change beta on that level. You can't change alpha. So, since it's max's turn, you can only change alpha, and it compares it to the 2 values you have here, right? Since these are the 2 possibilities, right? Either you pick 7 or you pick 5. Alpha wants to get the biggest number, so it picks 7. And that's it. Beta is not changed. Then here, we want to pick the biggest out of these. So between 7, 7, and 11, 11 was the biggest. Cool. Now we can go here and we can now recalculate this node, right? If we recalculate this node, we can see that it's min's turn. So we only change the value of beta. And if we look at min, right, we can see that it's between infinity, 11, and infinity. So obviously we pick 11 since that's the smallest. It's smaller than infinity. And what we have over here is a prune condition since alpha, wait, hang on. Do we? No, we don't. We don't have a prune condition. My bad. I think the goal is to find the best guaranteed options for each current path, doing it globally, passing up might prune incorrectly. Yeah, I think that's correct. So if alpha is greater than beta, we prune it. In this case, it's not, so we just continue doing what we're doing. So it's just one subtree left to do now. So just checking we've got that correct. So we did pick the smallest one there. Yeah, okay. And now we just pass in these values down. Yeah, it's greater than or equal to. So if the two are equal, as if, like, look, in this section here, the two were equal, so we pruned this branch. And we have alpha equals 7, beta equals 11, and we pass that down. Alpha equals 7, beta equals 11, and now we just do the final one. So here it's min's turn, meaning we change beta. Is it smallest to use 11, 9, or 8? We can clearly say it's 8, so it's no longer 11, it's 8. Now move that up, so if it's Max's turn, we can only change alpha. So what's bigger, 7, 7, or 8? Well, we can say 8's the biggest, so we can change alpha from 7 to 8. And from there, we can now go down and bring the values of alpha and beta down here. So alpha, beta equals 11. And essentially, from there, we can get that we can only change beta since it's min's turn. So is 11 small or is 7 small or is 10 small? So we can say 7 is the smallest. And from that, we can now recompute this one, which is Max's turn. So what's the biggest, 8, 8, or 7? 8 is still the biggest. And essentially, one thing that you'll notice here is that alpha is greater than or equal to the value of beta. So if there were more things here, you would actually prune them off. But there's not. That was the final stage, unfortunately. So no pruning. Why didn't you prune 12 here? Where is that? Let me just quickly check. Oh yeah, we would prune that. It's on the final one, so I didn't actually look at the prunings on that. But we would prune 12 there. Good spot, yeah, because alpha is greater than 5. Sorry, 7 is greater than 5. Good spot. And here we'd prune 10 as well. And essentially, if we continue up, we can get alpha's turn. So 8 is bigger than 8 and 7, so we're going to stay with 8 there. And in min's turn, we're going to pick between 11, 8, and 11. So this becomes 8 because that's the minimum one. And then finally on Max's turn, we're going to pick what's biggest, 7, 7, or 8. Well, 8 is the biggest, so essentially 8. The answer for like the best possible utility of this state would be 8. That's the answer. That's how you would get it. This was a very big example, but I hope it kind of hammered home the point of how we go about doing this. Does that all make sense? Have I done anything wrong? Do let me know. Have I missed any prunings? So when alpha is equal to beta, we also prune that too, as you did. Yeah, exactly. So the condition, as I said in my notes, was alpha is greater than or equal to beta, the node is pruned. So if this is true, the node is pruned. And finally, could you explain chance nodes? Chance nodes. I don't believe chance nodes were in the slides mentioned. Where have you got chance nodes from? No, I don't believe chance nodes are in the spec. Well, I mean, I don't know. It's not in any of the slides or the revision lecture or even in like the normal lecture. We didn't look at chance nodes. I'm not even sure what they are. But you know what? I haven't done that paper yet, so yeah, wouldn't be able to help you there, unfortunately. Yeah. Yeah. Well, in any case, is that if there's no more questions, I will end the recording here. And yeah, bye guys.